This is part 1 of the lecture on section 1.3 on the greatest common divisor in Euclid's algorithm. Euclid's algorithm is an algorithm for computing the greatest common divisor of two integers. We want to remind ourselves of how that algorithm works, discuss some applications, and finally prove that the algorithm is guaranteed to give correct results. Before we jump into the discussion of the algorithm, let's have a look at some background information and review some of the places we've already been. First of all, we've talked about divisibility. We say that if a and b are integers, then a divides b if and only if there is an integer q so that b is equal to q times a. Notice that if we write a divides b, we're making a logical assertion. We're saying that b divided by a is an integer. On the other hand, if we write this symbol, a divided by b, well, we're simply constructing a rational number from these two integers, a and b. Therefore, the symbol a divides b and the symbols a divided by b, though they look very similar, are really saying something that's quite different, so we want to be sure to distinguish them. There are some important theorems regarding divisibility. For instance, we can say that if a divides b and b divides c, then a divides c. In other words, divisibility is transitive. Furthermore, if a divides b and c both, then it divides any linear combination of b and c as long as the linear combination is composed with integers. This is straightforward to prove, and we'll use it so many times during this section it's probably worth reviewing the proof. mb plus nc could be written in terms of a because we know that b is divisible by a and c is divisible by a. If we do that rewriting, then we can factor the a off, and in this form it's easy to see that a does in fact divide the linear combination mb plus nc. Finally, we've introduced the division algorithm already. It tells us that if a and d are integers, where d is greater than 0, then there are unique integers, the quotient and remainder, that satisfy two conditions. First of all, the remainder is strictly less than this positive divisor and greater than or equal to 0, and a is equal to the quotient times the divisor plus the remainder. Just as a reminder, this a is called the dividend. Now finally, if we're going to be working with an algorithm to compute the greatest common divisor, we should have clearly in mind what it is. If a and b are integers, then the greatest common divisor of a and b is simply the largest of all of those integers that divide both a and b. Now, if a and b are not both 0, then the greatest common divisor has to be well defined. For instance, if we had the greatest common divisor of minus 12 and 18, well, the divisors of both 12 and 18 are these: 1, 2, 3, and 6, and of course all of their negatives: minus 1, minus 2, minus 3, and minus 6. Notice there is a largest common divisor. In general, if we took the absolute value of a and the absolute value of b, compute the maximum of those, nothing larger could possibly divide both a and b. Therefore, the greatest common divisor is well defined because there is always a maximum of the set of common divisors, and that set is never empty because, for instance, 1 would divide both a and b. Secondly, the greatest common divisor is always positive. That is because even if we selected a negative divisor, let's say for instance minus 3, it's true in this case minus 3 divides negative 12, it also divides 18, but the positive version, plus 3, also divides both of these, and plus 3 is greater than minus 3, so we would never select a negative number for the greatest common divisor. In this case, the greatest common divisor is 6. Finally, we should notice that the greatest common divisor is simply insensitive to both the order and to the signs of a and b. If I replace minus 12 by 12, well, I have exactly the same set of common divisors, plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. And it doesn't make any difference. Say if 6 divides 12 and 18, then it also divides 18 and 12. So order and the signs of A and B don't matter, and we come up with statements like this. Finally, we should remember that probably in grade school we learned how to compute the greatest common divisor of integers by first of all listing the prime factorizations of each of the two integers, and then picking out the maximum number of prime factors that belong to both of them. In this case, both have a 2 and both have a 3, so 6 is the greatest common divisor. We can talk about examples and applications of computing the greatest common divisor with the Euclidean algorithm, and we'll want to do a few things here. We want to compute the greatest common divisor of these two relatively large integers. We then want to work backwards through the Euclidean algorithm to write that greatest common divisor in the form of a linear combination of the two integers that we're working with. It turns out that the greatest common divisor here is 2. And then finally, we'll see that there are some implications about solving Diophantine equations. Diophantine equations are equations where we're looking for only integer solutions. Now, the Diophantine equations will be considered a little bit later after we've worked through Theorem 2 and its corollary, but we can get started with Euclid's algorithm right away. Suppose we wanted to compute the greatest common divisor of 2,462 and 462. What we do is to begin with 2462 and 462 and to apply the division algorithm to come up with this equation right here. 2,462 when divided by 462 gives a quotient of 5 and a remainder of 152. We can then promote the 462 to be the new dividend. The old remainder becomes the new divisor, and we apply the division algorithm again, this time getting a quotient of 3 and a remainder of 6. We now continue in this way, promoting the old divisor to be the new dividend, and promoting the old remainder to be the new divisor. We continue in this way until we get a remainder of 0. Once we've completed that process, the greatest common divisor is found by backing up one step. It's the smallest of the strictly positive remainders that we construct in this sequence of division algorithm statements. Now, our line that has the greatest common divisor can be reordered so that it gives us the greatest common divisor in terms of the last dividend and the last divisor. We've written that here. Now observe, we could do that with the previous line as well. This 6 can be written in terms of 152 and 462. By reordering, we've transformed our equation here from describing 2 in terms of 152 and 6 to describing it in terms of 462 or 152, which are the dividend and divisor from the second line. Well, the smallest now is 152. Using the first line, we can redescribe 2 in terms of 2,462 and 462. We do that by solving the first line for 152 and substituting here. So if we reorder, we have 2,462 times 76 plus 462 times minus 405 is equal to 2. In other words, we've expressed the GCD of 2,462 and 462 as a linear combination of those two integers, which is what we were asked to do in part 2 of this example. Finally, we'll need to be making reference to this simple fact a few times. If a and b are natural numbers, now of course that means they're both positive, then if a divides b, a must be less than or equal to b. This is intuitively obvious. For instance, we know that 6 divides 18. Well, certainly 6 has to be less than or equal to 18, or we wouldn't be able to do the division. We can prove this rigorously, though, in this way. If a divides b, then it must be the case that b is equal to some quotient times a, where that quotient is an integer that's greater than or equal to 1. Well, b then is equal to q times a plus 0, but we'll write 0 in this way, minus a plus a. Subtract this a from both sides to get this expression here after factoring the a off from the other two terms. Well, we know that q is at least 1, and it's an integer. Therefore, q minus 1 must be at least 0. A is positive because it's a natural number, so we have an integer that's at least 0 times an integer that's strictly positive. This product must be non-negative. Well, that tells us then that b minus a is non-negative, which is the same as saying that b is greater than or equal to a, and that justifies this little lemma that we'll be using occasionally as we work through the following proofs.